I'm excited to kick off today's presentation on fundamental piping design principles. Today, we'll explore key concepts like safety, reliability, operability, and compliance. Over the next few slides, I'll guide you through the essential considerations that ensure piping systems are safe, efficient, and compliant with standards. Let's get started. Now, let's take a closer look at the key objectives in piping design for refineries. First and foremost, piping systems must ensure safety and code compliance. This means adhering to standards set by organizations like ASME, API, and NFPA, which help us maintain a safe working environment and meet legal requirements. Next, reliable fluid transport is critical. Our piping must effectively carry fluids under various pressures and temperatures without failure, ensuring continuous operation. Additionally, maintaining operability and flexibility is essential. Piping systems need to accommodate thermal expansion and stress, so they can adapt to operational changes without causing damage or downtime. Finally, accessibility and maintainability are vital. Designing with ease of access in mind allows for easier inspection, repairs, and upgrades, ultimately supporting the long-term efficiency of the refinery. All of these objectives tie back to our overall goal: creating piping systems that are safe, reliable, adaptable, and easy to maintain, ensuring smooth refinery operations. When it comes to safety and routing principles, the first thing I want to emphasize is the importance of following established standards like ASME, B3013, API, and NFPA. These guidelines are designed to ensure safety and reliability across our piping systems. Next, it's crucial to maintain safe distances from hazardous lines. Keeping a safe separation helps prevent accidents and makes maintenance safer for everyone involved. We also need to install emergency isolation valves. These are vital because, in case of an emergency, they allow us to quickly shut off the flow and contain any potential issues. Another key point is keeping piping runs as short as possible. Shorter runs help reduce pressure drops, which improves system efficiency and performance. It's also important to separate hot and cold lines, hot being steam and cold being chilled water. Proper separation minimizes thermal interference and improves safety. Finally, for long piping runs, using pipe racks or routing utilities underground can be very effective. This not only keeps the piping organized, but also protects it from environmental damage and reduces clutter above ground. Overall, these principles help us design safer, more efficient, and more reliable piping systems that align with our project's safety standards and operational goals. Let's talk about thermal stress and expansion. As temperatures change, materials tend to expand or contract, which can create stress in the system. To manage this thermal expansion, we use components like loops, offsets, and bellows. These elements provide flexibility and allow movement without causing damage. Additionally, anchors, guides, and supports play a crucial role. They absorb and distribute loads that result from thermal changes, helping to maintain the integrity of the piping system. It's also important to check the stresses at critical points, such as pumps, turbines, and compressors. These components are sensitive to stress, and ensuring they are within safe limits is vital for reliable operation. Now, remember the formula for thermal expansion. Delta equals alpha times L times delta T here. Delta is the change in length, alpha is the coefficient of thermal expansion, L is the original length, and delta T is the temperature change. Understanding this helps us predict how much a material will expand or contract under different temperature conditions. Now, let's talk about pressure and flow design. When designing a piping system, it's crucial to consider the MOP, or maximum allowable working pressure, to ensure safety and reliability under operating conditions. This means we select materials and components that can handle the highest expected pressures without risk. Next, correct pipe sizing is essential, and we determine this using velocity guidelines. Maintaining proper flow velocity helps prevent issues like erosion, noise, or pressure drops. For example, if the velocity gets too high, it can cause wear and tear, so we need to choose the right pipe diameter to keep things running smoothly. Using control valves and reducers also plays a vital role in safe operation. Control valves regulate flow and pressure, ensuring the system works within safe limits. Reducers are used to connect different pipe sizes, maintaining proper flow and pressure throughout the system. To better understand flow velocity, we use the formula V equals 4Q divided by pi times d squared. Here, V is velocity, Q is flow rate, and d is pipe diameter. This equation helps us calculate and control flow speeds, which is key to designing an efficient and safe piping network. Overall, these principles, designing for MAWP, proper sizing, and using the right control devices, are interconnected. They help us create systems that are safe, efficient, and reliable, aligning perfectly with the overall goal of effective process design. Let's talk about the materials and structural supports used in piping systems. First, carbon steel is a common choice for transporting hydrocarbons and water because it's strong and cost-effective. When we need resistance to corrosion, especially with more aggressive fluids, stainless steel becomes the material of choice. It's excellent for handling corrosive or chemical services. Then, for high-temperature lines, alloy steel is preferred because it can withstand the heat without losing strength or integrity. Now, moving on to supports. These are critical to ensuring the piping system remains stable and functional. Supports include shoes, hangers, guides, and anchors. Their primary role is to prevent vibration and sagging, which could lead to failures over time. It's also important to consider external forces like wind, seismic activity, or even blast loads, as these can exert additional stress on the system. Proper support design helps us mitigate those risks and maintain safety and reliability throughout the plant's operation. All right, let's talk about safety devices and accessibility in our systems. First, installing pressure relief valves, or PRVs, along with drains and vents at the high and low points of the system is crucial. This helps prevent pressure buildup and ensures safe operation. Additionally, using steam tracing and insulation is essential to prevent freezing and coking, especially in colder environments, which can cause blockages and damage. Now, moving on to accessibility. It's important to place valves at operator height, around 1.2 to 1.5 meters, so they're easy to reach and operate safely. We also need to leave enough space around equipment for maintenance, making sure that our team can work efficiently and safely without unnecessary obstacles. Finally, implementing color coding and line tagging is a simple but effective way to improve safety and operational clarity. It helps quickly identify lines and components, reducing errors and increasing overall safety. When we combine these safety devices with good accessibility practices, we're creating a safer, more efficient system that supports our overall safety culture. Let's walk through this example of a cooling water line. We start with the given data, a flow rate of 0.01 cubic meters per second, which is roughly 160 gallons per minute. The pipe length is 100 meters, and its diameter is 0.1 meters, or about 4 inches. The water's density is 1,000 kilograms per cubic meter, and the friction factor we're using is 0.02. First, we calculate the velocity of the water inside the pipe. To do that, we divide the flow rate by the cross-sectional area of the pipe. The area, A, for a circular pipe is pi times the radius squared, which comes out to approximately 0.00785 square meters. So, dividing 0.01 by 0.00785, we get a velocity of about 1.27 meters per second. This is a crucial step, because understanding the velocity helps us determine the pressure drops caused by friction. Next, we look at the pressure drop along the pipe. Using the Darcy-Weisbach equation, the pressure loss is approximately 16,200 pascals, which converts to about 0.16 bar. This pressure drop is significant because it indicates how much energy is needed to pump the water through the system, overcoming friction losses. Overall, what this example highlights is how flow rate, pipe dimensions, and water properties all influence the pressure drop in a cooling water line. Recognizing these relationships is key for designing efficient systems that maintain proper flow while minimizing energy costs. Now, moving on to the results and their interpretation. The velocity we measured is 1.27 meters per second, which is well within acceptable limits. This indicates that the flow is steady and efficient without causing undue stress on the system. Next, the head loss over a 100-meter length is 1.65 meters. This is a key point because it tells us how much energy is lost due to friction and other factors along the pipe, which directly impacts pump requirements. The pressure drop is 0.16 bar, which is relatively low. This is good because it means the system doesn't require a high-pressure pump, reducing energy use and operational costs. Regarding expansion, the length increase is 72 millimeters. This suggests that a loop will be necessary to accommodate this expansion safely and prevent stress on the piping. Putting it all together, the conclusion is that we have a safe design with minimal pump load, thanks to the low pressure drop and controlled flow velocity. Additionally, the system provides the necessary flexibility to handle expansion and operational variations without compromising integrity. Overall, these results support a robust, efficient, and reliable system design.